here will be 1 by f, because Tp corresponds to the entire period of the signal. So instead of Tp is equal to 1 by twice f, it will be Tp equal to 1 by f. And therefore, there, this factor of 2 for the half wave rectifier is not going to be there. This factor of 2 will not be present for the half wave rectifier. So therefore, we see that the ripple voltage will be twice that of the full wave rectifier. The ripple voltage for the half wave rectifier will be twice that of the full wave rectifier. Okay. So this ends the part on the required filter capacitance to achieve a particular ripple voltage. And now we go to, I guess, Zener regulation. So we have met with Zener regulation before. Let us go to revisit the Zener regulation. Let us draw the ideal voltage so this is Zener, sorry, Zener. Okay. So this is my supply voltage. And across this my load resistance is connected. Okay, so this is my VZ and this is my IL, and this is my IA. So the function of this Zener diode is what? To maintain constant output voltage VL as much as possible. Okay, so this is IL. To maintain as much constant output voltage VL, when the load resistance RL varies or the load or the supply voltage VPS varies over a particular range. Okay, so what a specified range or over a particular range, if RL varies or if VPS varies, the output voltage VL should be held constant. So we need to know the proper input resistance Ri in order to make this circuit work, because you appreciate that Ri is the most significant component of a Zener diode circuit, because its function, its job is to prevent the circuit from burning out. Okay, so Ri has to be chosen appropriately such that the Zener diode is working in its rated region and it does not burn out to limit the current. So initially we can write Ri as VPS minus Vz by ii, and that is Vps. What is ii? ii is Iz plus IL. So let's call this Iz, the current through the Zener diode. Here it is Iz. So there we can write Iz plus IL. So Iz therefore is Vps minus Vz by Ri minus IL. So the diode current will be minimum, that is Iz will be minimum when Iz, this value of the current, will be minimum when Vps will be minimum and IL will be maximum. So on one side, the maximum tolerable Zener diode current occurs, sorry, the minimum possible Zener diode current occurs when Vps is minimum and IL is maximum, and that defines the region where the circuit, where the diode, the Zener diode has to work in the Zener breakdown region. So that will be the minimum current for which the Zener diode has to maintain working in the Zener diode region. It cannot come out of the Zener diode region. Similarly, the other extreme of the current is Iz will be maximum. Iz will be maximum when Vps will be maximum and IL will be minimum. So this defines the other extreme of operation, that is where the Zener diode current is maximum. All other conditions are in between these two conditions. So we can say Ri, so we can say that Ri Vps mean minus Vz by Iz mean, because when Vps is mean, Iz is mean, mean is for minimum, plus IL max. So this is one condition of for Ri, that is Vps mean minus Vz when Iz is also minimum and when IL is maximum. And then on the other hand, Ri has also to maintain, its job is to maintain the diode in the Zener diode region where the current IL is minimum, or when the Zener diode current is maximum. So that will be Vps max minus Vz divided by Iz max plus IL min. So then we just equate the two. This is equated to be that. So when we equate the two, we get Vps mean minus Vz times Iz max plus IL min is this is just cross multiplying and things like that. So just nothing else. Minus Vz times Iz min plus IL max. This is just obtained by cross multiplying. So we can assume that we know the range of the input voltage, that is the value of VPS mean and VPS max. This must be known. That is, what is the maximum possible outage of the input signal, or it is not signal, the input voltage. What is the maximum variation of the input voltage, the lower extreme and the upper extreme? And we also must know the lower extreme and the upper extreme of the load current. So what is the variation of the load current for which the output voltage Vz will be constant? Okay, so that also must be known. So these are specifications given to us. These will be specifications given to us, that you design this circuit such that the output voltage is maintained constant when the input voltage varies from such and such VPS mean to such and such VPS max, and the output load current varies from such and such IL mean to such and such IL max. Okay, so then also we must also know that for the Zener diode current, that we can design that the IL mean, IZ mean can be designed to be, let us say, 1/10 of IZ max. So this we will design that the maximum current passing through the Zener diode we are working here. So actually we are working pretty much straight. We are assuming this line is straight. So we need to know what is IZ. This is IZ mean and this is IZ max. Okay, just neglect this horizontal line. Okay, so just this is nothing. So we can design that IZ mean is 0.1 of IZ max, and therefore from here we can find the value of Vz. Sorry, we can find the value of IZ mean or IZ max. Vz is given. Vz is here, the Zener voltage. Vz is given to, we know the Zener diode. So we can find out IZ mean or IZ max. So if I find out, just again, you can just verify this at home. IZ max is IL max times VPS max minus Vz. Minus IL mean times VPS mean minus Vz times VPS mean minus 0.9 Vz minus 0.1 VPS max. Okay. So using finding Iz max, after we find Iz max, either we use this equation, we can find Iz mean, and either we can use this equation, or we can use this equation to find out the value of Ri. Because Iz max means IL mean, we can plug in Iz max here. VPS max is given, IL mean is given, Vz is given, we know Ri. Or we can from Iz max, we can find Iz mean. And once Iz mean is known, VPS mean is known, IL max is known, Vz is known, and therefore Ri is known. So this enables me to find out the value of Ri to make me work in the specified Zener diode range. So to maintain the output voltage constant when the input voltage varies from VPS mean to VPS max, and when the output current varies from IL mean to IL max. That is all. Now let us go to a definition of how well the Zener diode does this job of maintaining the output voltage constant irrespective of the change in input voltage or the change in output current. So let us draw this circuit. Basically the same circuit with the Zener resistance. In the previous circuit, so in the previous circuit, we assume that Rz, which is the Zener resistance, is 0. We assume that the Zener resistance is 0 means what? We assume that, as we said, this region was absolutely vertical to the x-axis or the voltage axis. We assume this, so that this was 90 degree. But in an ideal Zener diode, though this can be theorized or though this can be assumed, that is not true for a practical Zener diode. All practical Zener diode will have a finite amount of resistance, which means that this line, instead of going that, will be slightly this. So this slope corresponds to the 1 by Rz. Though the Rz is small, but this is true for a practical Zener diode, which is this. So the Zener diode combined with the Rz. So therefore, what will be its effect? Its effect is, though the RL, when the RL varies, in the previous example we saw that though the RL varies and though the VPS varies from VPS mean to VPS max, and RL varies such that IL varies from IL mean to IL max, the output voltage VL remains constant. That we saw in the previous example. In fact, we designed RI such that this event occurs. But now with the resistance RZ in place, such will not happen. That is, when the resistance RL is going to vary, or when the supply voltage VPS is going to vary, the output voltage VL is going to change slightly. Because this voltage does not stay constant as Vz, as we assumed before. It changes from Vz1 to Vz2. When you are here, Iz mean you are at Vz1, and when you are at Iz max, you are at Vz2. Because of this variation, the output voltage will vary somewhat. It is not going to vary a lot, but because this line, the red line here, it is still almost the oops. Oh, what happened? Okay. So this red line, okay, it has a small slope. So that is why it is going to, the output voltage is going to vary slightly. Let me draw the black line again. Sometimes this behaves in another way. So this is the black line. So then we define how well the Zener diode performs its job of maintaining the output voltage constant irrespective of the change in load current or the change in supply voltage by defining two terms. One is called source regulation, and that is delta VL by delta VPS into 100%. That is, with change in supply voltage Vs, how much the output voltage varies. So as you can well appreciate, for an ideal Zener diode circuit, delta VL is going to be 0. So for an ideal voltage regulator, the source regulation is 0. So the lower the source regulation, the better our Zener diode circuit is. The other definition is the load regulation, that relates to the change in voltage with the change in the load current. So that is VL no load minus VL full load by VL full load. So VL no load is the output voltage for zero load current. And VL is the output voltage, VL full load is the output voltage for the rated load current. That is, I mean, for the maximum rated current. Okay, so how much the voltage varies when there is no current through the circuit, IL is 0, and that is the load resistance RL is infinite, or the circuit is open circuited. RL is not there simply. Output current IL is 0 means RL is not there. And when I put the value, the minimum value of RL so that the maximum rated current flows through the load RL. So what is the difference in the output voltage VL under these two circumstances? So as usual, if it is for an ideal regulator or ideal voltage regulator, the load regulation will also be 0, and the minimum the load regulation, the better our circuit is, or the better the Zener diode has successfully maintained the output voltage constant irrespective of the change in the load current. Just a minute. Okay. So this completes our section on Zener voltage regulation. Let us now go to clipper and clamper circuits. So first of all, we will take clippers. As the name suggests, this word clipper, it means that it clips the output voltage. That is, it does not allow the output voltage to fall beneath a particular value or to be over a particular value. So in that sense, a half-wave rectifier is a clipper because it does not allow the output voltage to go below the 0 line. It gives me the output voltage which is constantly above 0. So the half-wave rectifier is an example of a clipper circuit because regardless of the variation in output in the input voltage versus time, we get the output like this. Neglecting V gamma and all the things, roughly speaking, we get the output as this. So the output voltage does not go below 0. So therefore, it is an example of a clipper circuit. So this can be used to limit the voltage to an electronic circuit. That is, let us say I do not want a particular circuit to experience a voltage which is above a rated voltage or below a rated voltage. I do not want the electronic circuit to experience those voltages, and therefore, under those circumstances, I can use a clipper to limit the voltage range at the output. So this can be used to prevent, for example, breakdown of transistors in a circuit. Okay, let us say for a particular transistor, we do not want the transistor to be more reverse biased than this value. So like that. So just take a very clipper circuits are very favorite in the minds of the interviewers, and they are relatively simple to analyze, provided you do some practice with them. Please do practice with clipper circuits. So I'll just draw some typical examples. So let us have a circuit like this. So this is R. D1 and V0 and here is my Vi. So what will happen? If the diode cut-in voltage is V gamma, if this diode has a cut-in voltage of V gamma, and if the input varies like this, so this is voltage versus time. So the voltage at this point, when the diode is on, will be VB plus V gamma. And when the diode is on, this voltage cannot rise above this value. If the diode is off, if diode D1 is off, that means the voltage at this point is less than VB plus V gamma. Then the current in the circuit is 0. And therefore, the output voltage will follow the input voltage. Sorry, if the diode D1 D is on, okay, if the diode D is on, therefore this voltage will be held at VB plus V gamma. And if the diode D1 is off, what is going to happen? There will be no current in the circuit, and the voltage here will be held at VB plus V gamma. So during the initial part of the circuit, when the diode D1 is off, because the voltage here has not risen sufficiently, when diode D1 is off, there will be no current in the circuit. And if there is no current in the circuit, there is no drop across R, and the voltage here will be held at VB plus V gamma. So this is here VB plus V gamma. So therefore, the output is going to follow this and this. Do you understand that? So this output voltage is clipped at VB plus V gamma. Once the diode starts conducting, here diode D1 is on, the voltage at this point X, the voltage at the output cannot rise more than VB plus V gamma. When there is no current in the circuit, the voltage drop across R is 0, and therefore the output voltage V0 follows the voltage Vi, because there is no drop across R. Therefore, this part is when the diode D1 is off. If you understand one, the others are very simple. It is the same thing. It is a very easy thing. Diode D1 off. In the initial part of the circuit, diode D1 is on because the voltage at the point X has to reach a minimum value of VB plus V gamma. And when the diode D1 is off, there is no current in the circuit. The drop across R is 0, and therefore the output voltage V0 will be the same as Vi. But when the diode D1 is on, the output voltage will be held at VB plus V gamma. It cannot rise more than VB plus V gamma. So the output voltage is clipped. at VB plus V. Now let us consider several other circuits.
Sir, when diode will be off, what will be the voltage?
Tell that again.
Sir, when the diode will be off, what will be the voltage? VB plus
The
V gamma.
voltage, when the diode is off, you see this voltage, the diode off is D1 is off, therefore there is no current in the circuit. If there is no current in the circuit, there is no drop across R. There is no drop across R, and if there is no drop across R, the output voltage V0. What is the output voltage V0? It is V0 minus VI minus IR. So if I is 0, there is no current. So V0 is equal to VI. Very simple. If there is no current in the circuit, V0 becomes equal to VI. And this state of affairs continues till the diode conducts. The moment the diode starts to conduct, the output voltage will be held at VB plus V gamma. It cannot rise more than that because the output voltage of an on diode, we are neglecting diode resistance. That we are neglecting. But the output voltage across an on diode is V gamma. So it will be VB plus V gamma. Okay. Now consider this circuit. We consider different circuits. So this is R and this is R. This is my V0 and this is my VI. Now see, this is the input waveform. Time T. So here, if this is VB, the voltage here is VB minus V gamma. Now, if the diode is on, mark this, if the diode is on, the voltage at the point X cannot fall more than VB minus V gamma. It cannot fall more than VB minus V gamma. So the output voltage will be so this voltage is so when the output voltage is more than VB minus V gamma, because this is the N side of the connected to the N side. If the voltage at the point X becomes more than VB minus V gamma, then the current through the circuit is 0. And if the current through the circuit is 0, then there is no drop. Again, the same old logic, that there is no drop across R, and therefore V0 becomes equal to VI, which is true for the red portion. This which is true for this portion. So the output voltage becomes equal to the input voltage when the diode D is off. And when the diode D is on, this is the diode D. And when the diode D is on, the output voltage cannot fall. It cannot fall more than VB minus V gamma. The moment the output voltage touches here, input voltage touches here, it starts to become lesser. The diode starts conducting, and the moment the diode starts conducting, the output voltage will be held at VB minus V gamma. It cannot fall more than that. Okay. You just need to practice this, and these are very good like areas where all kinds of interviewers for all different kinds of examinations, they set questions. Clipper and clamper circuits are very common for all kinds of examinations. They will just give you a circuit, input waveform, plot the output waveform. So please practice a lot of things, these things at home. It is not difficult, but you need practice. If you do not practice, you won't be able to do it, at least not in that time, and you will make errors. It is easy if you practice, it is difficult if you don't.
So the horizontal line was showing D on, right?
Tell that again.
Sir, the horizontal line was showing D on.
Yes, yes. Yeah, sorry, I forgot to tell you that. So let us mark it in green. So this is this part. Oops, okay. If something happens. I don't understand why this, some bug. Okay, so this is D on. So now let us go to another circuit. You apply the same logic. It is basically everything the same. Under different circumstances, you just apply the same reasoning. So this is again my VB. VO is R. And this is my VO. What will happen? Draw the waveform. So the output voltage here at this point, again the point X, will be minus VB plus V gamma. Now VB is usually much more than V gamma. V gamma is a small voltage, right? 0.7 volt or something like that. So we can write this as, to show that it is a negative voltage, minus VB minus V gamma. To show that this is a negative voltage. So we can write that negative voltage here. So this is the negative voltage. Minus VB minus V gamma. And what is going to happen? If the voltage if the diode is on, the voltage at point X, cannot rise above minus VB, above this voltage. The voltage at point X cannot rise above the voltage minus of VB minus V gamma, because the diode is going to hold that voltage constant. So when the diode is on, so therefore the diode on means the voltage does not rise above that value. But when the diode is off, Okay, when the diode is off, that is the voltage Vi is sufficiently negative. When the voltage at this point, it is lower than minus Vb minus V gamma, it is lower than that value, then the diode D, will be off. When the voltage at point X becomes lower than minus Vb minus V gamma, diode D will turn off, and if the diode D turns off, then again no current through R and V0 becomes equal to Vi. So voltage is lower than minus Vb minus V gamma, the output voltage will follow. Just a minute. So the output voltage is going to follow the input voltage. For voltages lower than minus Vb minus V gamma, when the diode D is off, then the output voltage is going to follow the input voltage. Okay, so here in this part, for this part, again for this part, I should draw that also in red. So diode D is off because the voltage has input voltage has fallen. It has become lower than minus Vb minus V gamma, and the horizontal portion here and there is where the diode is on. Let us take another example. What is going to happen? You can draw the input waveform. So the voltage again at the point X, it will be minus Vb minus V gamma or minus of Vb plus V gamma. So let's draw this minus Vb. First of all, let us mark this demarcating point when the diode is on. When the diode is on. So this is a negative voltage. So minus of Vb plus V gamma. So therefore, if the voltage at the point X is below minus Vb minus V gamma, this diode turns on, the diode D turns on. When the voltage at point X falls below minus VB minus V gamma, and therefore the voltage at point X cannot fall below this voltage because the diode D is going to turn on. When the diode D is off, and when the diode D is off, when the voltage at point X is above minus VB minus V gamma, because the voltage at point X needs to fall below minus VB minus V gamma in order to turn D on. When the voltage at point X is above minus VB minus V gamma, or this voltage, okay, then the diode D is going to be off. And if the diode D is off, the same old reasoning, V0 becomes equal to Vi, drop through R is 0. And therefore, this is the region where the output voltage is going to follow the input up till this point. Up till this point. This is the region where the diode D is off. And then what is going to happen? From here, let me draw the, sorry, let me follow that, sorry, it's better. Doing same things for that. This is the point where the diode D turns on, and again the voltage follows. So this is the period over this period, okay, diode D is off. The voltage is more than minus VB minus V gamma, and over this period, whenever I draw that, black line vanishes. So diode D is on. This was the original black line. Simple as that. Now we can have two circuits. Okay, and this is Vi. So what is going to happen? And let me draw the voltage waveform. So the voltage at this point, if you mark the, first of all, mark the transition voltages. Here it is. VB1 plus V gamma due to this branch, and here it is due to this the transition voltage is minus VB2 plus V gamma. Assume that both the diodes have the same cut-in voltage. So minus VB2 minus V gamma. So minus VB2 plus V gamma. So mark the transition voltages. First of all, you mark the transition voltages. So this is voltage versus time. Mark the transition voltages. Here it will be VB1 plus V gamma, and here it will be different, minus VB2 plus V gamma. So the voltage at point X, this is the point X. The voltage at point X cannot rise over VB1 plus V gamma. VB1. It cannot rise above VB1 plus V gamma because the diode D1 is not going to allow the voltage at point X to rise above VB1 plus V gamma because diode D1 is going to conduct. So the output voltage will be here like that. Not rising over VB1 plus V gamma. Okay, assume the red curve to follow the black curve. Okay, just a bit mess. Here it is following the black curve. Similarly, the diode D2 will make sure that the voltage at point X does not fall below minus VB2 minus V gamma. Because when the voltage at point X falls below minus VB2 minus V gamma, diode D2 starts to conduct. And when diode D2 starts to conduct, the voltage at point X is held fixed at minus VB2 minus V gamma. So therefore, it comes here, and then the diode D2 starts to turn on, and therefore here it stays constant. Again, it goes here, stays constant, comes here, goes here. So here, in this region, D1 off, D2 is also off. In this region, D1 is on, D2 is off. In this region, again, both are off, D1 is off. So the voltage V0 becomes equal to Vi, D2 is off. In this region, D1 is off, D2 is on. And then again in this region, it is the same as this region, which is original. Both the diodes are off. D1 is off, D2 is off. Simple, nothing to worry. You practice, you would like the clever questions because they are nice to play around with. Okay, please wait. Okay. Now let us turn our attention to another class of questions where the battery source is in series. If you remember, in all our previous situations, this battery source VB1 was in the parallel branch or in the shunt branch. Here, you note all these circuits. Battery is in the shunt branch. Battery is in the shunt branch. Same. Battery is in the shunt branch. All other questions cases we dealt with, the battery is in the shunt branch. Now, this has to be distinguished from the case where the battery is in the series branch. If the battery is in the series branch, it is no less, it is the same level of difficulty, provided you follow some simple rules. For example, if this is my source, and let us say there is an R and there is a diode. So this is my plus side and this is the minus side of VB. This is my R. And this is my input voltage Vi. So what you do, whenever you plot this, this is my input waveform. Now, whenever you see the battery in series, the first thing you do is you plot the waveform at the input of the circuit after the battery. You plot the voltage just after the battery. So the voltage at point X here, X1, let us say. Let us call this A. Instead of X1, let us call this A. You plot the voltage at point A. So what it will be? Vi minus Vb. So let us plot that voltage. This is the voltage at point A. Vi minus Vb. So this is Vb. Now you go to the previous analysis. When the voltage at this point X, when it tries to fall below 0, we assume the diode cutting voltage is 0. If the cutting voltage is V gamma, we can accordingly do minus V gamma. But if I assume the cutting voltage is 0, when the voltage at point X, assuming the diode cutting voltage V gamma to be 0, assuming V gamma to be 0, when the voltage at point X falls below 0, the diode won't allow that to happen. The diode will keep that voltage fixed at 0 because the diode is on now. The voltage at point X has tried to be below 0. So therefore, this part of the waveform is going to be clipped. So output voltage draw here. So this is the output voltage here. So it does not allow the diode to conduct, it does not allow the voltage to fall below 0. The output voltage, which is the voltage at point X, it does not allow the voltage to fall below 0 when the diode D is on. So here the diode D is on in this part. And in this part, running out of colors. Okay, wait. Very good. Very good. More color. Okay. So in this part, oh, yellow is not all the same. Okay, wait. Take pink. So for this part, the diode D is off. And when the diode D is off, the output voltage V0 follows the voltage at point A, which is the red curve. Understood? As simple as that. If you understand one, you understand thousands. Okay. Diode D is off, the output voltage follows the voltage at point A, and diode D is on, the output voltage does not fall below zero. As simple as that. Let us continue this idea. So again, the same thing. The diode, the voltage source is in series. So you plot the voltage at point A. This is my original waveform. Voltage at point A is VI minus VB. Again, the voltage at point A. Now what is going to happen? When the diode conducts, that is, when the voltage at, assuming the diode cut-in voltage is zero, diode D, assume it's V gamma to be zero. Assume it's V gamma to be zero. So when the diode D conducts, the output voltage V0 will be the same as the input voltage at point A. You now forget the black curve. Whenever the battery is in series, after you have drawn the red curve, you forget the black curve. Now you forget what is to the left of A. Once you have drawn the red curve, you forget what is to the left of A. You concentrate on point A and point X only. Then when the voltage at point A is greater than 0, the diode conducts. And if the diode conducts, the voltage at point X becomes equal to A, equal to the voltage at point A. And when the voltage at point A becomes lesser than 0, the diode D does not conduct. And if the diode D does not conduct, there is no current in the circuit. Again, there is no drop across R, and therefore the voltage at point X becomes equal to 0 because there is no drop here. VR becomes equal to 0. If VR becomes equal to 0, the voltage at point X becomes the same as ground, which is 0. This is my ground. So therefore, when the diode conducts, the voltage at point X follows A. Therefore, the same waveform we got before. Here the diode D1 conducts. Let me draw the output waveform. So this is the output waveform. In this period, which is here and here, the diode D is on. In this period, the diode D is off because the voltage at point A is lesser than 0. The diode D is off, and if the diode D is off, the voltage at point X is the same as ground. Okay, so we don't care whether the diode is in the series or parallel or everything. We apply the reasoning. We only care at the outset of the question. You only care whether the voltage source is in the shunt arm or in the series arm. These two we only need to see. If the voltage in the series arm, you just plot the voltage after the battery, and then you forget what is to the left of that point. You concentrate only to the right of the point. Next one. Sorry. Again, so now the voltage at point A is VI plus VB. So therefore, you draw that waveform at point A. and this is VB. So in this circuit, when the voltage at point A or when the voltage at point X becomes again less than 0, the diode conducts, and it is not going to allow the voltage at point X to go below 0. So any voltage below 0 will be clipped. Any voltage below 0 will be clipped because the voltage at point X cannot fall below 0, and therefore the output waveform will be simple. In this part of the circuit, on this part of the circuit, the diode D will be off. Because it is connected to the N side is connected to the point X. So the diode D will be off. The moment it hits 0, or if you take V gamma, the moment it hits minus V gamma, 0 minus V gamma, the moment it tries to fall below that, the diode is not going to allow that. So therefore, the voltage at this point will be, again, please assume that will be where the diode is on. Diode is on. Draw the red color. This was the red color. Should not go below this. This blue should not be here. The blue should rise from here. Okay. Simple. Then the last one in the clipper domain. So again, this is the point. This is the point X. Draw the input waveform. Okay. Mark the voltage at point A, which is VI plus VB. So the voltage at point A Now you see, if I look at the point A, when the voltage at point A becomes lesser than 0, the diode D is going to conduct. But when the voltage at point A is more than 0, the diode D is going to be off. And if the diode D is off, the current in the circuit is 0 and the voltage at point X becomes equal to 0, which is the voltage here. So therefore, the voltage at point X does not rise or does not go above 0, because going above 0 makes when the voltage at point D, or we can say like this, when the voltage at point A becomes less than 0, okay, the diode conducts and the voltage at the output becomes equal to the voltage at point A. But whenever the voltage at point A rises above 0, so it won't allow to rise, because whenever it tries to rise above 0, the diode D switches off, and whenever the diode D switches off, the voltage at point X will be the same as the ground potential, because the drop across R is 0. So therefore, the voltage at point X never rises above 0. So like that. In this part of the circuit, or in this part of the circuit, the diode D is on, because when the diode D is on, then the voltage at point X becomes equal to the voltage at point A. And during these parts of the circuit, or here, the diode D is off, because when since the voltage has just become 0, the diode has just become reverse biased, and when the diode becomes reverse biased, the current in the circuit becomes 0, and the PD, or the potential difference across R, becomes 0. The voltage at point X becomes equal to 0. Okay, so these are just examples of Clipper circuits and how the Clipper circuit behaves. Let us now go to another class of circuit called clampers. And this is rather simple. It is an AC source. VI is an AC source. I should write it as this. And we have a diode, capacitor in the series arm and diode in the parallel arm. So what will happen? let us name these voltages. The voltage across the capacitor VC. Sorry, this is V0. This is ground. So if my input voltage is like this, the voltage, follow the voltage at this point again. The voltage at point X, as the capacitor charges in this period, it is going to be held at 0. Oh, it's the same problem. So the voltage at the point X, as the capacitor charges, the diode conducts, the voltage at point, assuming the diode cut-in voltage is 0, the voltage at point X will be held at 0. At this point, the voltage at point Y starts to fall. But when the voltage at point Y starts to fall, the capacitor has to discharge. Again, remember the filter circuit, but with the difference here, because the capacitor and diode are in series resistance, so the capacitor cannot discharge. In the filter circuit, we had the discharge path for resistance, and the capacitor was in the shunt arm. Here, there is no discharge path for the capacitor. So as the voltage at point Y starts to fall, the capacitor voltage the voltage across the capacitor will be held at the maximum value, which is here. So let us suppose if this curve is given by Vm sine omega t, the output voltage will be equal to Vm sine omega t minus Vc. So that will be Vm sine omega t minus Vm, because the capacitor has charged to the maximum voltage Vm. So this is the voltage across the capacitor at the end of the first quarter cycle. This voltage is going to stay the same because the capacitor during this period of time cannot discharge. So the voltage across the capacitance is going to stay at minus Vm, which is why the output voltage is going to be now Vm sine omega t minus Vm. So just follow this. The voltage now is going to fall. It is going to fall like this. So that means the DC level of the signal is changed. The DC level of the original signal was 0. The DC level of this clamper circuit is changed. The maximum voltage is 0. The maximum output voltage is 0. So we can shift the DC level. This can happen. This can be very useful in various circumstances, like when the signal loses DC level during transmission. Let's say a signal, information signal, we need to adjust the DC level of the signal. or restore the DC level of the signal, which can be lost due to transmission. So we can use a clamper circuit to do that. Now we can have another variant of this.
Sir.
Yeah.
So can you please explain the previous one once again?
Yeah, I will. So for the previous circuit, you see that in the first quarter wave, concentrate on the first quarter wave of the signal, which is from here to there. The capacitor charges. The output voltage remains at 0 because this diode, assuming it has a cut-in voltage of 0, will maintain the output voltage to be 0 because the diode is conducting. The capacitor is charging up. So the voltage at point X remains at 0, which is why the red curve is at 0. This is the charging phase of the capacitor. Now, when the voltage at point Y starts to fall, the capacitor has to discharge. But the capacitor cannot discharge because if the capacitor has to discharge, current has to flow in this way. But this is not allowed because we have the diode here. So the capacitor cannot discharge. And if the capacitor cannot discharge, the voltage across the capacitor has to stay constant. So what is the voltage across the capacitor? The voltage across, on one side, the black curve, we have VI. So it is VM. The maximum voltage here at the end of the quarter cycle, the maximum voltage at this point is VM. Or the voltage at this point at the end of the quarter cycle is VM. The voltage at this point is 0. So the capacitor is charged up to a voltage VM. So the output voltage will be Vm sin omega t minus Vm because the voltage across the capacitor will always be Vm here. So that is why we have this minus Vm term. So Vm sin omega t, which is Vi minus Vm. Okay. So therefore, the output voltage is now going to, whatever happens to the output, whatever happens to the input voltage, the output voltage is going to follow. Because the voltage across the capacitor has to be held at Vm. Voltage across the capacitor will be held at Vm. So whatever happens here, this will happen. The voltage at point X will be voltage at point Y minus Vm. So this is the waveform, the red one, which is that waveform, which is the voltage at point X. Okay. Too many pages. Okay, let's go to the next one. I need to delete something. Is there a way to go to the next page? Okay, but delete. Okay. So here in this case, we have a battery source VB and we have the diode V0, Vi and the capacitor. So here The voltage, the only difference is that the voltage at point X will be held at, assuming the diode cutting voltage is 0, will be held at plus VB. So during this time, the charging part, the voltage at the point X will be held at plus VB. And then when the capacitor voltage Vi starts to reduce here, the moment it crosses here, again it's going to start like this. So we can, you see, we can shift the DC level to be any value, not just the maximum can touch 0 as in the previous circuit. In the previous circuit, the maximum voltage touches 0 here. The maximum voltage here touches 0, but we can shift that level. We can shift the maximum voltage to any value. Here the maximum is at VB. The same will happen for a square waveform. So this is VF. So if this is Vi, so we can have VO, which is this. So this will be VB. So this one is VO. So this is an example of how to shift the DC level of a signal. And this can be used when we are receiving a signal. When the transmitted signal loses the DC level during the transmission, we can reset the DC level at the receiver. This is its practical usage. Now, let us go to the general form of diode circuits. Analysis of diode circuits. And this is rather simple, not difficult at all, but you have to again get used to it. Multiple, we can call it multiple diode circuits. How to analyze a circuit when several diodes are present? Let us take a typical example. Let's call it D2. Let's call it D1. So this is ID1. This is ID2. This is IR1. This is R2. And this is IR2. Then we are given R1 is 5 kilo ohm, R2 is 10 kilo ohm, V gamma is 0.7 volt, V plus is 5 volt, V minus is minus 5 volt. And we have to find out what is the value of V0, ID1 and ID2 for two cases. One, Vi equal to 0, and number 2, Vi equal to 4. Now here again, we have just one principle which you have to follow, and you cannot go wrong. The beauty about these kinds of circuit is that you cannot go wrong. If you follow the proper steps, even if you try to be wrong, you cannot be wrong. And what is that? The first thing you have to do is to estimate the state of each diode, because there are multiple diodes and the circuit is there is a particular voltage, they are connected to resistances and multiple voltage sources, multiple diodes. So we do not have a clear view as to what will be the whether the particular diode will be in the off state or on state. If we do not have a clear knowledge whether a particular diode is going to be in the on state or off state, we assume the state of a diode. So the first step is, where is that? Assume the diode conduction state. That is, either it is whether it is off or whether it is on. Doesn't make sense. Now in this decision making, because we are assuming, we can be wrong. That means you assume that the diode is in the off state, but actually your assumption is wrong. So you perform the circuit analysis assuming the diode is in the off state, and at the end of the circuit analysis, if you find that the results contradict your standing, that is, if your diode D1 is in the off state, that means the voltage across the diode D1 should be less than V gamma, or the current through the diode D1 should be equal to 0. But if you find after the circuit analysis that either of the two or both of the two are violated, that is, the voltage is greater than V gamma, greater than or equal to V gamma, and the current across the diode, the current flowing through the diode is positive from the P side to the N side, then you will assume, then you will deduce that your initial assumption that the particular diode is off is wrong, and then you revise your assumption, you change your assumption, and then perform the circuit analysis again. And at the end of each circuit analysis, you have to re-verify the state of every diode. When such questions are given to you, you will not get full marks if you do not re-verify your conjecture or your state, even if your answer is correct. Your marks will be deducted. Please mind this very carefully. Your marks will be deducted even if your answer is correct. If at the end of the answer you do not verify that the original assumptions you make during the diode conduction states are indeed true. So if you originally assume that diode D1 is on and diode D2 is on and perform the circuit analysis, at the end of it you have to justify that indeed the diode D1 is on and the diode D2 is on, and then therefore say that the above answer is verified to be correct. Unless you do this step, even if your answer is correct, you will not get full credit. Please mind this very carefully. This is all. So what do we do? What we can do, however, is we can try to see the voltage levels and try to make a studied estimate as to the state of a diode. Because if you make a wrong estimate, nothing is going to happen. You are going to deduce that your estimate, you are going to discover that your original assumption is wrong, and then you have to redo the analysis. But in order to avoid that, we can sometimes look at a circuit and try to assume the state of a doubt to make sure, to make at least a studied, not sure, but to make a studied estimate, so that we may not have to revise our answer or revise our state of conduction of a doubt or correct the state of conduction of a doubt. So we try to make a studied estimate, but doesn't matter. Even if you go wrong, if I follow the proper procedure, I will get the correct answer. So don't overly get biased or overly spend time on finding out exactly what will be the doubt states. Try to look at the circuit, make a studied estimate. Okay, if it clicks, you get the answer in one shot. If it does not, you have to revise it again. So here you see the doubt, the voltage V is at 5, V plus is at 5 volt, and the voltage V minus is at minus 5 volt. Now the voltage V1 is at minus 5 volt, and the doubt voltage VI is 0. I do not know what will be the state of conduction of D1 though, because if you assume that the diode D1 is on, okay, if you assume that diode D1 is on, because you will argue that here you have 0 and there you have a negative bias, that is a kind of a minus 5 volt, and there this minus 5 volt is going to be minus 2 volt here. So diode D1 may be on, I don't know. But if the voltage here becomes, if the voltage here becomes more than, you know, like 0.7 volt, then the diode D1 is going to turn off. So we don't know. So let us assume the diode D1 to be off. Let us try to see. Assume. You can assume a different thing. There is no fixed way to analyze the circuit. Somebody can assume that diode, let's assume diode D1 is on and carry out the analysis according to his or her way. So if diode D1 is off, you can find the current IR1. IR1, which is equal to, over this loop, KVL across this loop, KVL across this loop. So IR1 will be equal to V plus minus V gamma, drop of diode D2, D2 drop, minus V minus by R1 plus R2. All these values are given. V plus is given, V gamma is given, V minus is given, R1 and R2 are all given. And when you compute this will come out to be 0.62 milliampere. So the output voltage V0 will be what? It will be V plus minus I1 R1 minus IR1 R1 and if you plug in the values, it will come out to be 1.9 volt. And therefore the voltage at this point, which is called V dashed, the voltage at this point will be V dashed is given by P naught minus V gamma, because the diode D2 is on. there is actually not a big way why diode D2 should not be on, because on one side is connected to 5 volt, the P side is connected to plus 5 volt, the negative side is being connected to minus 5 volt. So in all probability diode D2 is on. Okay, so therefore my voltage V plus is V0 minus V gamma, and then that is equal to if you plug in the value of V0 and V gamma, it will turn out to be 1.2 volt. So if V0 is V prime is 1.2 volt, and our Vi was 0 volt. So we are doing for this case where Vi is 0. So Vi is 0. Vi is 0. That is 0. And this is V prime. V prime is 1.2 volt. That means the diode D1 is indeed turned off, because N side is connected to 1.2 volt and P side is 0. So therefore diode D1 is indeed off, and therefore we verify that our original assumption is correct. So this you must be writing in your examination paper. So therefore D1 is verified to be off. And the analysis is valid. Okay, let us stop here. The time is up. We'll continue from here. Let's wait. Download the attendance list. Okay, I'm ending the class. You can leave.
Thank you, sir.
Thank you, sir.